So okay, welcome back. In the last video, we have discussed that the energy of the potential energy. So okay, welcome back. In the last video, we have derived that the potential energy of interaction E between the magnetic dipole mu and the external applied uniform magnetic field B0 is equal to mu into B0, and mu is equal to, we know that Gn into E divided by 2mp into I cross into B0. But we know that the vector I has the orientation from minus I to plus I, and I am denoting these values as mi. Therefore, the angular momentum vector I is actually mi h cross or h by 2 pi. And substituting this here, we get this is equal to Gn E divided by 2mp mi h by 2 pi into B0. Okay, that is equal to Gn into Eh divided by 4 pi mp mi into B0. And this term, that is Eh divided by 4 pi mp, is called a nuclear magneton. That is Gn. This term is denoted as Bn into mi into B0. That is beta n. Beta n is called the nuclear magneton. That is, it is equal to Eh divided by 4 pi mp. Okay, and this beta n is a nuclear magneton. So the difference in energy between the energy level, and this is the equation for energy. So for delta E, actually mi has a value from minus I to plus I. Therefore, for each value of mi, there is an energy. Okay, for energies become degenerate in the presence of an applied magnetic field, these orientations have different energy. Therefore, each mi value has different energy. Okay, and mi has, we know that, increases from minus I to plus I by adding 1 each. That is, difference between two mi values is equal to, that is, delta mi is equal to plus 1. Actually, mi is equal to minus I plus 1, minus I plus 2, like that. So, difference between the successive energy levels is delta mi is equal to plus 1. So, delta E is equal to Gn into beta n into B0 into delta mi. And for adjacent levels, delta E is equal to Gn into beta n into B0. Delta mi is equal to 1. And according to selection rule, according to quantum mechanics, selection for magnetic transition, NMR transition, is delta mi is equal to plus 1. That is, only transition between the adjacent levels is possible. Therefore, delta E is equal to Gn into beta n into B0. Okay, that means the energy for transition is proportional to the applied magnetic field. Energy for transition is proportional to applied magnetic field. And transition between nuclear magnetic energy levels can be induced by the use of electromagnetic radiation having the frequency that corresponds to the separation between these energy levels, that is delta E. That is, we know that the frequency of transition, nu, that is delta E divided by h, is equal to Gn into beta n into B0. And by applying this frequency, we can undergo transition from the nuclear magnetic energy levels. And this phenomenon is called nuclear magnetic resonance. And here, the interaction is actually between the oscillating magnetic field of the electromagnetic radiation. Magnetic field of the electromagnetic radiation. Therefore, it is called, this transition is called the magnetic dipole transition. Magnetic dipole transition. Unlike the other spectroscopy technique, in other spectroscopic techniques like IR and UV visible spectroscopy, the interaction is between the electric field of the radiation and electric dipole moment of the system. But in NMR, the interaction is between the oscillating magnetic field of the radiation and magnetic dipole moment of the system. That is what is called a magnetic dipole transition. Magnetic dipole transition. Okay. Then this is the resonance condition. That is by applying a frequency equal to Gn beta n into B0 undergo transition, and there is a resonance condition, or there is a Bohr condition for the transition. And we know that the energy levels of nuclear magnetic energy levels are equally spaced, because the Mi energy is equal to we know that the Gn into beta n into Mi into B0, and this Mi differs only by 1 unit. Therefore, the energy levels are equally spaced. Therefore, in NMR's transition, a collection of identical non-interacting nuclei would give a single NMR absorption frequency. In NMR spectrum, we get a single absorption frequency for a collection of identical non-interacting nuclei. Okay, then this equation shows that the electromagnetic radiation required to effect a transition between nuclear magnetic energy levels depends on the strength of the applied magnetic field. Unlike the other spectrum, in other spectrum we not require the presence of an applied magnetic field, but in nuclear magnetic transition we require the presence of an applied magnetic field. If you consider hydrogen. Hydrogen has Mi is equal to, so I is equal to half. Therefore, Mi values are only plus half and minus half. Therefore, the energy levels split in the presence of an applied magnitude. That is, I is equal to plus or minus half. In the absence of applied magnetic field, there is no field. That is B equal to 0. Then these two levels are degenerate. But in the presence of an applied magnetic field, these levels splits. That is, when B is equal to B0, this become Mi is equal to plus half, have lower energy, and Mi is equal to minus half, have higher energy. And the difference between these energy levels is equal to Gn beta n into B0. Okay, that means the energy actually depends on, it is for at a particular field strength B0, the energy difference is like this. Energy actually depends on B0. We can draw the condition is like this. That is, energy versus magnetic field strength. Magnetic field strength, the actually graph will be like this. That means with the increasing field strength, the energy difference also increases. Delta E increases. Delta E increases with the increasing B0. At a particular B0, it's a constant. With increasing B0, field increases or the energy difference increases. We can draw, understood that by this diagram. Okay. And for practical reason, the field applied are normally in the order of 1 to 5 Tesla. B0 we are normally applying a value of 1 to 5 Tesla. Okay, for a value of B0 is equal to approximately 1.5 Tesla, nu equal to 60 megahertz. Or when B0 is equal to approximately 2.5 Tesla, we can calculate using that equation, it will be 100 megahertz. And these values come under radio frequency range. Therefore, nuclear magnetic transition can be achieved by using radio frequency radiation. Okay, that's all we are discussing in this video. The other points we will discuss in the next video. Okay, all right. Read your textbook well and understand the topic much. Okay, thank you.